Hello, I'm Pushkar, Master Teacher in Chemistry at Vedantu, and I'm discussing KVPY 2018 SX Part 1 Chemistry paper. Here's a question. The correct representation of wavelength intensity relationship of an ideal blackbody radiation at two different temperatures, T1 and T2, is option A, B, C, and D. I think these two options, B and D, are immediately discarded because we know for the black body radiation, if we plot a graph of intensity versus lambda, so you always get, if this is at temperature T2, you'll always get the temperature T11 completely inside the temperature T2. Completely inside if T2 is greater than T1. So in any case, this B and D is absolutely correct. Why it is completely inside? Because when you increase the temperature, for every wavelength, in absolute sense, the intensity of related to every wavelength increases. Okay, because if you're increasing temperature, then obviously they are going to produce more energy, more radiation. So at any wavelength, if you compare, then the intensity at I1 will be less than I2 for any wavelength. So that is why that's the property of the black body radiation. That's very important thing. So we can rule out this B and D option. Now we are left with two other options, T2 and T1 and T1 and T2. If you look at the peak, if we look at the peak of these graphs in option C, and if we look at the peak here also, and if we compare that T2 is greater than T1, so we know that T2 is greater than T1. In that situation, the C option is absolutely wrong, because if T2 is greater than T1, then how come this line is below this line? Because common sense that more heat at high temperature, more radiation will come out. More radiation will come out. So option C is also discarded. Only option A is the correct option. So very simple question. Let me discuss something more about this. That in black body radiation, the shape of the graph is like this. That was studied by Rayleigh Jeans and many other scientists, and Wiens and Stephen and Boltzmann, and they found that if you compare it at two different temperatures, suppose this is temperature T2 and this is temperature T1, where T2 is greater than T1, the wavelength corresponding to these peaks, let's call this as lambda 2 max, and let's call this as lambda 1 max. That means the maximum the intensity corresponding to the lambda, there is one particular lambda at which the intensity will be maximum. That's called lambda max. So we have a relation that this lambda max is always equals to some constant divided by T. That means it is inversely proportional to the absolute temperature of the black body. There is intensity on y-axis. So as you can see that as the temperature is increasing, this lambda 2 max is less than lambda 1 max. We can clearly see that lambda 2 max is less than lambda 1 max, and in fact the ratios are equal to T1 by T2. That relation will hold. That's a law which was proved by, kind of justified by Mr. Planck. And so he has given a theory, Planck's quantum theory, to justify this. And also very interesting to know that this justification could not come from the wave theory of light. The justification come from quantum theory of light. So first of all, this is very clear. And secondly, this the shape, if you integrate that shape, that means the area under the graph is equal to what? Total intensity, or the total intensity, I should write, or total power emitted must be proportional to T raised to the power 4. Absolute temperature raised to the power 4. So if this is T1 temperature and this is T2 temperature, if we talk about the area under the graphs, okay, so of course, if we talk about the area under the graph, then we can say that A2 upon A1 will be T will be equal to T2 upon T1 raised to the power 4. You're going to get this idea. Okay, what is A2? A2 is the area under this curve. And what is A1? If we want to show the A1 with different color combination, let me show. The A1 is this. So that's a very interesting topic. And this topic is called blackbody radiation. And this is the basis of, this is the starting point of all quantum mechanical thought processes. From this, in order to prove this, Planck has given a theory of Planck's quantum theory. And then things started and getting ahead. And now there is a full-fledged quantum mechanical theory for an atom. So I hope that you understand this, enjoyed this. Thanks for watching. Answer is A. Stay tuned for detailed discussions of such questions.